And just to remind you guys too that we have, for those people that need it, we have lots of resources for you guys out there. Besides coming by and seeing me or seeing Joseph, we also have every Friday, we have our personal, just for our class and any other class 1 out of 10 actually, is in Fretwell 113, we have our review session every Friday at 2 o'clock. So if you need help, come seek help. We also have right across from the math department, open tutoring in the Math Resource Center, Math Learning Center, literally right across from the math department. You can come up there and just walk in with your questions, raise your hand, grads come over there and help you out. We also have PALS, the new name of the supplemental instruction. And these are the locations for supplemental instruction. They do it Monday through Thursday. Monday from 2 to 3 is in Macy 201. Tuesdays from 11:30 to 12:30 is Fretwell 120. Wednesday from 4 to 5 it's in Macy 201. And Thursdays from 11:30 to 12:30 is back at Fretwell 120. So there's lots of places to get help, as we were just mentioning our test results and stuff. And a lot of folks, I mean, a third of the class literally was in the A range on this thing. But from that, we had a bunch of folks that just trickled down on it. So if you need help, get help. We got it. We're offering it to you, but it's up to you at this point. You've got to go seek that help and stuff. I mean, I can't make you go. You've got to do it yourself. I mean, we give you the opportunity and give you every resource to do it, but if you guys don't do it, you can only blame yourself. So, all right, so let's pick up where we left off last time. We were working on table integration stuff. And so with table integration, we're going to be using our tables to figure out what kind of, how to integrate some things. And I did this one because, number one, it's got lots of parts to it. And the second thing is a lot of folks have a difficult time finding this particular formula. All right, so first things first. On this particular problem, I've got the integral of e to the x divided by 81 minus, now e to the 2x, we know that when we see something like that is what? E to the x squared dx. And when I look at this problem, and I'm thinking about using a table, because clearly not a form I have memorized, I'm looking at the form of this guy, and I see this a squared minus u squared look in the denominator. And so that's the approach I'm going to take on these things, especially when I'm using the table integration type, because they're put into particular sections, and that a squared minus u squared is one of your major sections on this one. So here, the a squared would be equal to 81, and the u squared would be equal to e to the x squared, which is the same thing as that e to the 2x if you think about it. And so therefore, a would be 9. However, what's u equal to? If u squared equals e to the x squared, what is u equal to? E to the x. Literally take the square root of both sides. Now, here's the part that a lot of students forget. This is u substitution. So once you do u, then you got to do du. So what's the derivative? What's the derivative of e to the x? E to the x dx, but I don't care if it's a constant or a function or anything. I'm going to solve for dx in this stuff. Solving for dx would make 1 over e to the x du equal to dx. So when I substitute, this would turn into the integral of 81 was a squared. E to the 2x, or that e to the x squared, was u squared. I've got an e to the x on top, and the dx gets to be replaced with 1 over e to the x dx. Du. Literal substitution. These two guys held over. This is from the moving from the constant dx is equal to 1 over e to the x du, and that e to the x numerator holds over. What happens to my e to the x's? They cancel. If they did not cancel, then I can go back and replace an e to the x with u, but in this case, they happen to cancel. Does that make sense? So this turns into the integral of 1 over a squared minus u squared du. And so there's no constant to manipulate on this guy. All I got to do is go find the formula. So when I start looking for the formula, I traditionally go to the a squared minus u squared page, and the a squared minus u squared starts on number 30 there, and you'll notice that you don't see 1 over a squared minus u squared. And the reason why you don't, this is the other thing I wanted to do this problem and why we put it on our notes, is it's actually at the beginning. The integral of 1 over a squared minus u squared du is actually formula number 19. So in terms of formula numbers, this is formula number 19 that we're using out of our table. And formula number 19 says this is equal to 1 over 2a times the natural log of the absolute value of u plus a over u minus a plus c. And I'm literally copying formula number 19 now. Does that make sense? Now the next thing I got to do here is back substitute. So this would be equal to 1 over 2, and what was a equal to? A was 9, times the natural log absolute value of u, but u was equal to e to the x plus a, which is 9, divided by u, which is e to the x minus a, which is 9, plus c. So cleaning this answer up, the answer is 1/18, the natural log of the absolute value of e to the x plus 9, divided by e to the x minus 9, plus c. And going back and answering the web work aspect of this thing, what did we let u equal to in this particular problem? E to the x. And what formula did we use? Formula number 19. And the other thing that I want to show you guys, because of these crappy fractions and the like and the absolute values, how do I type this in on web work? Because you know that's what you're going to have to do in this particular section. I'm going to type it in like this. This will be equal to parentheses 1 divided 18. I always put parentheses in fractions. 1/18. Natural log parentheses ABS parentheses. ABS for the absolute value. And then I've got a fraction. So I've got to have a parenthesis for the numerator. E to the x plus 9. Close parentheses. Divide parentheses. E to the x minus 9. Close parentheses. And then I close parentheses for the fraction, and the close parentheses for the denominator, close parentheses for the absolute value, and then close parentheses for the natural log part, and then they give me the plus c. So this is how you would literally type it in on web work. Does that make sense? Questions? It's not overly difficult, but I've had a lot of students come by and complain about this one because they couldn't find the formula. That's because they were looking in the u squared minus a squared, or in this case a squared minus u squared look, but the fact is it was actually at the beginning, formula number 19. So don't forget, if it without that radical, they're typically in the first 20 problems you're supposed to have memorized, but the last couple we don't have memorized. Does that make sense? Well, today's big lecture is about next section. Section 6.5. And that is numerical approximation. So let me just give you the lowdown here. All right, so chapter 6. What have we done in chapter 6? Well, 6.1 was actually from the first test, and that was basically after we teach you guys u substitution. Chapter 6 is all about other techniques of integration. We taught you guys integration by parts. If the problem looks like integral looks like a product, and then maybe you want to try this integral of u dv equals uv minus integral of v du. Okay? But what if that doesn't work? Well, in case you had a fraction, we had the whole concept of partial fractions. What if partial fractions didn't work? Well, we did skip over the section on trig substitution. We went to, by the request of the engineering department, table integration. So if worst comes to worst, go look in your tables. Somewhere there's a formula that hopefully is just similar to what you got. But your tables are based on u substitution. So we're continuously beating to death u substitution. Well, what about this? What if we got a problem that I don't care what you do, you can't integrate it? There's no table answer. Because the actual problem is it's not integrable. There is no antiderivative for a particular function. And we got some of those functions out there in the universe too. And sure as anything, as you being a senior in mechanical engineering working on this stuff, you're going to come across one of those problems that doesn't have an integral to it. What do you do then? Well, as long as you got bounds, we can still do what we call numerical approximation. Now, this is an approximation. Now, we've already done approximation before. It's called Riemann sums. We did left Riemann sum, right Riemann sum, and midpoint Riemann sum. Out of those three, which one was the best? Midpoint. Well, we're going to take those concepts and extend on it. So midpoint was your best. So we focused on midpoint. But then in this particular section, and hopefully you'll watch the awesome pre-section video on this stuff, there's two other forms we're going to focus on. Now, midpoint you've done before, but there's going to be the trapezoidal rule, and then there's going to be something called Simpson's rule. Now, let me get down and understand what this section's all about. We're talking about a numerical approximation. We're talking about we're going to approximate an answer. We've got an integral with bounds. As long as we got bounds, we can get an answer out of this guy. But this is an approximation. It's not going to be exact, because if I want exact, I got to do a Riemann sum and take the limit as n approaches infinity, and I don't want to take an infinite number of partitions. So what do I want to do? I want to approximate this thing, which means I'm not going to an infinite number of partitions. We're going to go back to what we did in chapter 5.1 and 5.2. We're going to do so many partitions, 10, 20, 100, million, whatever. We're going to do, but we're going to cut it off at some spot. No, I'm not going to do a million, but we do have computers these days. Think about it. But I don't want to do that. So what do you consider, listen to my words, what do you consider a good approximation? What is the definition of a good approximation? Well, we're going to have some kind of a tolerance. We got to get this piston within a certain diameter. We got a certain tolerance, 1/10,000th of an inch or something like that. We got a tolerance. So we got to get our setting in there. So as long as I can get my tolerance, I don't care about the 15th decimal place on this thing. I'm good enough on 8 decimal places or whatever. I got to get my certain tolerance. So what we consider to be a good approximation is to get that tolerance with as few partitions as possible. I mean, I know I can take 2 million partitions and I'll get within my tolerance, but I don't have the time nor the inclination to do 2 million approximations and be able to add that kind of crap up. I want to do it quickly with few approximations. That's what this section is going to do for you. We got midpoint rule, trapezoidal rule, and Simpson's rule. Now, again, if you watch the awesome pre-section video, I did these problems and discussed the concept with you guys, as well as the Simpson's rule. And so I'm going to start with the main idea and the algebra review on this stuff, and I'm going to generate these formulas again for you guys. So let's take a look. All right. The graph of the absolute value function, absolute value of f of x, is a reflection of the original function, f of x over the x-axis and into the first and second quadrants. In case in point, if I wanted to take the absolute value of this particular function right here, if the function is x squared minus 2, the absolute value of that very much takes anything that is below the x-axis and literally reflects it across the x-axis and makes it positive. So this part's positive, so it just stays it there, leaves it there, but this little negative function right here would flip up and become a positive. So it reflects it across the x-axis. That is what the graph of an absolute value graph looks like, okay? So if we wanted to graph this guy here, all right, 1 over x cubed. Well, I just want to show you the relationship. Well, 1 over x cubed looks like what? Well, if you don't know, let's grab our calculator. 1 over x cubed. So I'm going to go to y equals, clear, and go 1 divided by x cubed. Now notice I'm not doing the absolute value first. I'm going to do a zoom 6, zoom standard on this thing. Whatever you can see it. And right at 0, it does not exist, right? So 1 over x cubed looks like this graph. Put it up here so you can see it. As you get very close to 0, it blows up. And as you farther away on the x-axis, it goes towards 0. And on the negative side, it does the same thing, but 1 over negative is still negative. So it goes towards negative infinity. So here's your y-axis, here's your 0. This is what the graph of 1 over x cubed looks like. Does that make sense? But now the question is, what does y equal that f of x, which is the absolute value of 1 over x cubed? Well, stuff that is above the x-axis is going to look the same thing. This region is above the x-axis. The graph is going to be identical. However, the region that is below the x-axis is going to reflect across that x-axis, and it's going to look exactly the same, except it'll be in the first or second quadrant. It literally reflects across the x-axis. This is what the absolute value graph looks like. Absolute value of 1 over x cubed. Does that make sense? That will be helpful in later sections here. So, when we look at, give the absolute maximum value of the function 1 over x cubed on the interval between 1 and 5. So over here, this is my graph, y equals absolute value 1 over x cubed, but all we care about is between 1 and 5. So here's 1 and here's 5. We know what the general shape of the function is. I'm just going to plot these points. 1 over 1 cubed. 1 cubed is 1. 1 over 1 is 1. 5. 5 cubed is 125. 1 over 125, absolute value of that is still 1 over 125. So this is 1 over 125. And knowing what the graph looks like is going to be this kind of L-shaped looking thing. It does this. So when we talk about the absolute maximum value, value from calculus 1 is the y-coordinate. Okay? So, where's the biggest y-coordinate? Where's the point with the biggest y-coordinate? And what is that y-coordinate? So the absolute maximum value of f of x, which is absolute value of 1 over x cubed, on the interval between 1 and 5, is what? What's the answer? 1. It's the y-coordinate. Anytime you ask for a value, they're looking for a y-coordinate. That y-coordinate maximum is going to be 1. That'll be advantageous to us in this particular section. Does that make sense? All right. Now, take a look at this function right here. The famous e to the x squared. If I go and try to integrate e to the x squared dx, you know what the answer is? This thing doesn't have bounds. You can't integrate it. It does not exist. For all those folks that used to have, higher power calculators like the T89, this is one of those things used to frustrate students because that has a symbolic manipulator. You put that thing in the integral of e to the x squared dx on the calculator, and the question shows that in the answer. It just gives you back integral of e to the x squared. It can't integrate it because it's not integrable. And there are lots and lots and lots of functions out there, just like this one, that I can't integrate it. But as long as I got bounds, so this is what the function looks like. And you're thinking, well, sure you can. Can't you use U substitution? Well, no, you can't. Knock yourself out. It don't work. It boomerangs back, and you don't get the answer back in the question and stuff. What about integration by parts? Nope, doesn't work. Doesn't matter what you do. Nothing works on this thing. And there's lots of functions out there that you can't integrate it. But as long as you got bounds, you can approximate it. So, just to remind you guys, this particular problem right here, we want to integrate from 0 to 1 of e to the x squared dx. So, we're going to approximate this thing. All right, so we're going to use n equals 4. So here it comes. Time to review a little bit. First thing I want to do when I want to do a Riemann sum is this. Remember, the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum as I goes from 1 to n of f of x I times delta x. There is the famous Riemann sum formula. But for us, we're going to set this up by just doing the sum as I goes from 1 to n of f of x I times delta x, because we're going to stop at a certain amount of n's. How many partitions we're going to do on this one? 4. And numbers I like 4, 6, 8 at worst. I don't like to go beyond 8 personally, but I can do 10 and 12 if you pay me enough. But 100, 1,000,000 and stuff like that, no, then I'm going to get into my computer science and start programming some stuff in here. I can get the computer to do it, but I don't want to sit there and do it by hand. Okay? So, here we go. Remember this. What is the formula for delta x? B minus a divided by n. What is the formula for xi? It is a plus I times delta x. Does that make sense? So in this problem, when you look at it, A is equal to 0, B is equal to 1, and I always start with delta x. That means delta x is going to be B minus A over N. N is 4 in this problem because they gave it to me. So that would be 1 minus 0 divided by 4, which means my delta x is 1/4. And I went ahead and drew this one out, but usually I just draw it out myself. We're starting at zeros. Here's my A. My delta x is 1/4, 0.25. So I went over 0.25, go over another 0.25, go over another 0.25, and I'm going to stop at 1. Here's my B. 1, 2, 3, 4 partitions. We know that when we want a lower or upper estimate of this guy, we use the left or right Riemann sums. However, when we want a better approximation, we use the midpoint. So, what are the midpoints? To calculate a midpoint, you add the two endpoints together and divide by 2. 0 plus 1/4 divided by 2 is 1/8. That would be, I'm just going to do 1/8. I can point it 625 if you want me to. I can do that on the calculator, sure. See, 1 divided by 8 is just 0.125, all right? So this would be 0.125. What's between 1/4 and 1/2? So I'm adding together 0.25 plus 0.5, add together and divided by 2 is 3.75. You'll catch a pattern on this after a while. What's between 1/2 and 3/4? 1/2, 0.5 and 0.75. 0.5 plus 0.75, add them together and then divide that by 2 is 0.625. And last but not least, what's between a 3/4 and 1? I'm going to take 0.75, add it to 1, and then divide that by 2, and I get 0.875. These are my midpoints. Does that make sense? So to do the Riemann sum, the midpoint for 4 partitions, I'm going to sum up the f of xi's times delta x. But in this section, once again, we have to, quote, show our work. So this would end up becoming, this would be equal to f of your first midpoint, 0.125, plus f of your next midpoint, 0.375, plus f of your third midpoint, 0.625, plus f of your last midpoint, 0.875. All that times, and I factored out the little delta x, and I put it on the corner there. All right? So, to show my work, we want to see you guys plug these numbers into the function. What is the function that I'm plugging into in this problem? What is the f of x? Where it's e to the x squared. We're using this method to integrate this guy where we can't integrate it. How many times have I given an easy problem and asked them to do a midpoint Riemann sum? They actually integrate it, and then they try to plug those numbers into the integral. You made a double integral. Congratulations. Welcome to Calculus 3. But no, we're just doing, you don't integrate the guy. This is actually the function that we're going to plug into, and this will get me approximate what that integral would be. So this would be equal to e to the 0.125 squared plus e to the 0.375 squared plus e to the 0.625 squared plus e to the 0.875 squared. All that times delta x. And what was your delta x in this problem? 1/4. 0.25 if you want to. So now, time for a crappy calculator problem here. Let's put it together. Parentheses. E to the 0.125 squared plus e to the 0.375 squared plus e to the 0.625 squared plus e to the 0.875 squared. And then I got to close the parentheses and multiply that times 1/4 or 0.25. So the only way you screw this up, honestly, is your inability to plug numbers into a calculator. What do we get? I get the answer 1.44874561. Got a question for you. is this the exact area under this curve between that curve, e to the x squared, and that x-axis, between 0 and 1? No. It's an approximation, but it is a good approximation. Does that make sense? It's probably good out to about, 3 or 4 decimal places before I get some error in there. Does that make sense? Okay? Turn the page. Well, since the midpoint rule, and the purpose of the midpoint rule was when you do the middle, and if you got some kind of a concave up or concave down function, the goal is that the midpoint, your errors end up canceling. Half of it will be an overestimate, other half will be an underestimate, and so you kind of average them together, and hopefully you cancel out some of your errors. Well, depending on the steepness of the graph and stuff, we came up with another formula called the trapezoidal rule. Now, trapezoid, so instead of using rectangles, which is length times width boxes here, we're going to use trapezoid. And remind you that the area of a trapezoid is equal to 1/2 base 1 plus base 2 times the height. Whereas this would be base 1 and base 2, this was your height. And we drew this picture like this because that's the way we draw these trapezoids in the Riemann sum process. You may know the trapezoid better as this: 2 parallel lines and 2 non-parallel. This is your base 1, this is your base 2, but we're going to be turning these guys on their side, and this is what and that h is actually going to end up being my little delta x, and the b1 and b2 would be the functional values of the endpoints. Does that make sense? So, here, we're supposed to use the trapezoidal rule to estimate with n equals 4, to estimate this integral from 0 to 1 of e to the x squared dx. Okay? So, here we go. First thing I'm going to do is calculate my delta x. My delta x is equal to b minus a divided by n. That is 1 minus 0 divided by 4, or 1/4. So I'm starting out here at 0, and then I move over a quarter, and then I'm going to move over another quarter, makes it a half. I'm going to move over another quarter, makes it 3/4. I move over another quarter, and I'm at 1, and there's my b. And honestly, when I'm doing Riemann sums, I don't personally care what where the function is. F of x is equal to e to the x squared. It's some kind of thing looking like that. But what I'm really focusing on is that x-axis and how I'm partitioning it. Now, here we go. To do the trapezoidal rule for 4 partitions, this would be equal to, we've got to think about this trapezoid up here, so between 0 and 1/4. But the area is going to be equal to 1/2 times your base 1. Your base 1 is going to be f of 0 plus base 2, which is f of 1/4. All that times your delta x. This is basically your base 1 and your base 2 ends up becoming f of 0 and f of 1/4. Does that make sense? That's going to be the area, using this formula right here, of this first partition. I'm trying to show you a pattern here. So that'll be plus. The next one is the next partition would be 1/2 times f of 1/4, which gives you your base 1, plus f of 1/2, your base 2, and all that times the height, which is your delta x. Plus, the next partition is going to be 1/2 times f of your first partition, 1/2, plus f of the second partition, 3/4, okay, times your delta x, plus one more, and that's going to be 1/2 times f of 3/4 plus f of 1, that times your delta x. Kind of squeezing them in there, but there's your delta x. So I did this 4 times, but we're looking for formulas. What's the first thing you notice about this thing? First off, every one of these terms has something in common. There's actually 2 things in common. What are those 2 things? The 1/2 and the delta x. So I'm going to factor that out. So I get T4 to be equal to basically 1/2 of delta x, or delta x divided by 2, times, now watch this. The rest of it is just going to be the internal points. It'll be f of 0 plus, watch this. This is f of 1/4 here, but notice the last endpoint becomes the first endpoint on your next partition. So they end up doubling up. It'll be plus 2 times f of 1/4, plus your 1/2 here, and another 1/2. So These guys, you got two of those, so you got to double those up. That'll be 2 times f of 1/2 plus, you got f of 3/4 and f of 3/4. That'll be 2 times f of 3/4 plus, and then you got 1 f of b. And there's a pattern for this, and this is the trapezoidal rule pattern. The formula is delta x divided by 2 times f of a. This is your f of a plus 2 times f of all the internal partition points. 2 times f of 1/4 plus 2 times f of 1/2 plus 2 times f of 3/4. And then you got plus over here, the 1 is actually b. The endpoints of a and b only show up once. All the internal points on your partition will show up twice. That's the trapezoidal rule. So here we go. Plugging my function and stuff here, remember, delta x was equal to 1/4, and my function is e to the x squared. Does that make sense? So, here we go. T4 will be equal to 1/2 times delta x. Delta x is 1/4 times f of 0, that would be e to the 0 squared, plus 2 times e to the 1/4 squared, plus 2 times e to the 1/2 squared, plus 2 times e to the 3/4 squared, plus 1 e to the 1 squared. At this point, it's time for the handy dandy graphic calculator here. And so, I'm going to go ahead and clean it up. What's 1/2 times 1/4? 8, so that'll be 1/8 times e to the 0, and I can put parentheses around 0, squared over arrow, plus 2 times e to the parentheses always run fractions, 1/4 squared, plus 2 times e to the 1/2, parentheses 1 divided by 2 squared, plus 2 times e to the 3/4, parentheses 3/4 squared. And notice when I put in the decimal, I didn't put parentheses around it. But with fractions, you got to put parentheses around it. And if you got something negative, you got to put parentheses around it. 3/4 squared, and then plus e to the 1 squared. And then enclose my parentheses. So that is exactly what I got here, except the 1/2 times 1/4 is where I actually put the 8th from. Now, when I hit enter, this is going to give me another approximation to this integral from 0 to 1 of e to the x squared. This was the answer 1.448 when we did the midpoint rule, and so I'm expecting something close, and let's see what I got. Yep, it is close. So I got, for my T4, that's trapezoid for 4 partitions, I got 1.490678862. Does that make sense? And notice I was comparing it to the other answer. I'm not expecting the same thing because they're different forms altogether, but I do expect something close. So when I'm doing these kind of problems and I get one answer to be 3.2 and the ot answer to be 98 point something, no, I screwed up somewhere. I'm expecting them to be relatively close. So always keep that in the back of your mind. And so in this trapezoidal rule formula, I try to show you the pattern, but now I'm going to give it to you. Here's my pattern. To estimate the integral from a to b of f of x dx, where a equals x0, b equals xn, and delta x, of course, is equal to b minus a over n, the formula for trapezoid is delta x divided by 2 times f of a plus 2 times f of x1 plus 2 times f of x2 plus plus 2 times f of xn minus 2 plus 2 times f of xn minus 1 plus f of b. It's f of a plus 2 times f of all the internal points plus f of b. There's my pattern on the trapezoidal rule. Does that make sense? Questions? So, if we got to analyze this, okay? We got a midpoint rule and we got a trapezoidal rule. Which one's better? Well, you would think because that's the second one I talked about. It must be better because we introduced it last. But actually, after you analyze a little better, you'll discover that the midpoint rule is actually better. Slightly better. That idea of the area when you go right in the halfway between the area below and the area above, canceling helps you out. When you do the trapezoid, here's the problem. Let's say I've got a function that just arbitrarily is increasing up, okay? Depends on the curvature. This is concave up. So if I do a trapezoid, and I'm just trying to do this one big, so here's your x1 and here's your x2, and you plot this point, and you make a trapezoid, and I'm exaggerating this, but you make a trapezoid, it's going to be a straight line. And so you're finding the area of the trapezoid. So if the curvature is concave up, it's always going to be an overestimate. You see, because you got that error right in here. And if the concavity of your function happens to be down, let's say, from A to B, and you do the trapezoid out of that guy, it is going to be an underestimate, because this is what you're actually calculating over here, and you're going to be an underestimate. The nice thing about that midpoint was, half of it's up, half of it's down, so you got your errors canceling each other out. And that still is more advantageous for us. So, well, then why even do trapezoid rule at all? Well, good point, but you'll see later why. But here's the other deal. So what we decided to do in terms of mathematics was, okay, let's do the best of both worlds, because trapezoid has some benefits to it. Midpoint is actually a little bit better. So what they decided to do was come up with the famous Simpson's rule. Simpson's rule is a combination of both the trapezoid and the midpoint rule. And to let you guys know where it really comes from and how it was derived, this is the deal. If I take 2/3 the midpoint rule plus 1/3 the trapezoid, I'll put this little n here, trapezoid rule for n partitions. 2/3 the midpoint rule plus 1/3 the trapezoid rule, because that's kind of this is a weighted average. The midpoint was better than the trapezoid. So by how much? Well, I'm thinking about 2/3. So 2/3 the midpoint plus 1/3 the trapezoid rule will actually give you Simpson's rule better for twice the number of partitions. So if this was 4 partitions you did the midpoint rule for, and you did the trapezoid rule for 4 partitions, you put those two things together, that actually will give you the Simpson's rule for 8 partitions. And we all know the more partitions the better, but the best type of way of approximating integration is going to be the Simpson's rule if you can use it, because it's a combination of both of them. And let me talk about the best. Fewer partitions, better accuracy. I can do few partitions and still get very accurate on my answer. That makes it the excellent system. The only problem with the Simpson's rule is this. You see that 2n right there? The way the pattern is formed, you must have an even number of partitions. For Simpson's rule, you got to have an even number of partitions. So I can do partitions of 6 and 8. I cannot do a partition of a 7 or a partition of 5. It won't match up mathematically, okay, with the 2/3 and the 1/3 algebra trick. So to give it to you guys, this combination, when you work on the algebra and beat it to death, n has to be even. And here is the Simpson's rule. It is delta x divided by 3 times, and here's your pattern. It is f of a plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus 2 times f of x4 plus plus 2 times f of xn minus 2 plus 4 times f of xn minus 1 plus f of b. Your f of a and f of b only show up once, and your internal points, your internal partitions are a 4, 2, 4, 2, 4 pattern. You start with a 4, and because n is even, you'll always end on a 4 just before your endpoint. So that's why n has to be even, and this is actually the Simpson's rule. Okay? Now I'm going to change this problem a little bit, because every year I tell people I'm going to change this problem, but I forget to do it on the notes. So I'm going to change it for you guys, because this is just bad. We try to make it, I can tell you what happened. I was typing this stuff up, and I was, looking at this thing, and I'm looking, look, I wanted to have nice points to plug in. So I'm going from 0 to 6 and n equals 6. What's my delta x going to be? 1. That's nice. 0, 1, 2, 3. Here's your problem. Just plug in 6 in this function. That'll be e to the 6 squared. What's 6 squared? What's e to the 36? something that's off the chart in terms of your calculator, because it's already on the overflow button in terms of e to the 36th power is some crappy scientific notation. Sorry, that was my fault. So we're going to make this thing 1 and make you guys do fractions. We're going to compare it to what we were doing before. But I want to do a Simpson's rule so you can catch a pattern. So I'm integrating from 0 to 1 of e to the x squared dx. This is still a function that is not integrable. So the only way I can actually calculate this integral from 0 to 1 of e to the x squared dx is I've got to use one of my Simpson's rule, midpoint, or trapezoidal rule. I want you guys, since I'm using n equals 6, the best approximation for this is going to be Simpson's rule. So here we go. Your delta x is equal to b minus a over n. So this, because I changed my b to 1, it'll be 1 minus 0 divided by 6, or 1/6. Okay? So here we go. 1/6. So now I'm going to put my little partitions out here. And this is 0. I move starting at a. This is my a, which is 0. I go over a 1/6. I do another 6. That's 2/6, also known as 1/3. I'm going to go over another 6. That's 3/6, also known as 1/2. I go over another 6, and that's going to be 4/6, which is 2/3. I go over another 6, which is 5/6. I go over another 6, which makes it 1, and there's my b. And just to confirm, 1, 2, 3, 4, 5, 6 partitions. A is 0, B is 1, the 1/6, the 1/3, the 1/2, the 2/3, and the 5/6 are all my internal points. So to use Simpson's rule for 6 partitions, the formula is delta x divided by 3. I'm going to write it out for you guys. Delta x divided by 3 times f of a plus 4 times f of x1 plus 2 times f of x2 plus 4 times f of x3 plus plus 4 times f of xn minus 1 plus f of b. It's a 4-2-4 pattern. And you've always got to end on a 4 for your last partition, internal partition point, before your f of b. So, in terms of this problem, this is going to be equal to delta x, and delta x is equal to 1/6 divided by 3 times f of a, which is 0, plus 4 times f of your first internal point, which is 1/6, plus 2 times f of 1/3, plus 4 times f of 1/2, plus 2 times f of 2/3, plus 4 times f of 5/6, and that is my last internal point, 5/6, before my b, and it's just one of those, plus 1 f of 1, plus f of b. This is what we want to see. We want to make sure when you guys are showing us the work on this stuff, you write down the formula, you plug the numbers into the formula, and we also, for full credit on this problem, I want you to plug the numbers into the function because I want to see what you're calculating. This would be S6 would be equal to 1/6 divided by 3 is what? 1/18, right? My function is still, hasn't changed. We beat to death a dead horse here. E to the x squared. So this would be e to the 0 squared plus 4 times e to the 1/6 squared plus 2 times e to the 1/3 squared plus 4 times e to the 1/2 squared plus 2 times e to the 2/3 squared plus 4 times e to the 5/6 squared plus e to the 1 squared. That is my answer. That's what we're looking for in terms of the answer for the problem. But we got one more hoop to jump through, and that requires the calculator. So I'm going to stick this thing in on my calculator, and let's see what we get. I'm going to do this because it's kind of nasty off screen here. E to the x squared. All right. When I did it, I got 1.4628735. And that, you notice it's really, if you look at the other answers, which you should be close to, it's right in the middle between those two guys. And this is a much better approximation. Does that make sense? It is actually accurate to kind of without out to the tenths, 10 thousandths or 100 thousandths position, actually. Does that make sense, though? Simpson's rule is the best. But the drawback on Simpson's rule is you got to have what kind of partitions? Even. All right. So in a nutshell, here is the entire formula to summarize here. We've got the left Riemann sum, the right Riemann sum, which is just your sum of f of x times delta x. You got the midpoint where you got to put in the bars. Here is the pattern for the trapezoidal rule, and here is the pattern for Simpson's rule. But the drawback on Simpson's rule is you got to have an even number of partitions. And you're looking at the same, well, can I always, instead of doing 5, doing more, I'll do 6 instead. Well, yeah, but let me show you some problems that you're going to do later on. What happens if you got a problem like this? What's the function? We don't have a function. We have input, output off of a computer program. We got some girl speeding down a highway in her fancy red Porsche problem. And all we got is data points. We've got these data points. Does that make sense? And if you look at data points, how many partitions do I have? I've got 1, 2, 3, 4, 5, right? Number one, can I do Simpson's rule on this problem? No, because I got 5 partitions. Well, can I do trapezoidal rule on this problem? Or can I do midpoint rule? Which one's better? Let's do the hierarchy. What's the best one? Simpson's rule, if you can use it. After that comes what? Midpoint, and then comes trapezoidal rule, and my last resort is left or right Riemann sums. So if I can't do Simpson's rule, I'm going to do midpoint. But to do midpoint, you've got to create a midpoint. See, I don't know what the value is at 1. Since I don't know the data value, I can't use it. So to create a midpoint, I got to go from 0 to 4, and then from 4 to 6 to get the midpoint to be 2 and 4, and that actually gives me less partitions, and that's going to be less accurate. So I can't do midpoint on this one because it's a chart. Does that make sense? So what's the best one going to be? Trapezoid. And if you read the problem, we'll tell you, yeah, you're right, the trapezoid is the best approximation. So there's a reason for why we have to do, because every one of these guys that we're doing has a particular purpose. But if I have my druthers and I can do any number of partitions I want to do few partitions with most accurate, I'm going to go Simpson's rule. But I got to have an even number of partitions. So the next section, well, I know we're finishing up today, but the next section that I'm going to talk about, because this is a big section here, the next section within the numerical approximation is how to figure out this error-bound stuff. How do I figure out how accurate I need to be? Because here's the real deal. How many partitions do you really need to take? Do you need 4? Or will 6 do? Or do I actually need 100? Or do I need 1,000 partitions to get that tolerance to be within 0.000001 so I can actually calculate something or other? It depends on what your tolerance is. These formulas are designed to help you figure out how many partitions you need to have to be within a certain accuracy. And if you look at the second part, you've got this error-bound thing, this idea of the maximum value of the second and fourth derivative is what this K is going to be. We'll talk more about that next time. Go ahead and get started on this midpoint, trapezoid, Simpson rule stuff, and we'll talk more about that and look for something special from me in the next class. See you guys then.